Log on, tune in, find out. Another good idea from Cambridge.
Our second talk this afternoon, Peter Kim, another student from the University of Missouri, who's going to talk to us about optimizing combination therapy under a bivariate Weibull distribution and with an application to the responses being toxicity and efficacy. Okay. Over to you.
Right. Okay. Okay. Hello, everybody. Thank you for coming. Especially before I get started my talk, I really thank you to Rosemary for inviting me, and especially I really very thank you for my advisor, Dr. Flournoy. It's very honored to study with you. Thank you about that. Okay, so let me get started on my talk. So today, my talking is I'm gonna talking about the optimizing combination therapy under a bivariate Weibull distribution. So I will use the bivariate Weibull distribution, okay, with the application to toxicity and efficacy, okay, responses. Okay, so this is my outline. So I will just explain about the contents, general idea. So key idea is I will explain about the binary outcomes. Then second, I will explain about the why we should use the bivariate Weibull distribution. Okay. The third case, using the bivariate Weibull distribution, I will just define the outcome probabilities. Then using outcome probabilities, find the likelihood, and then find the information matrix. Okay, so that is my plan. Okay. Okay. So let's think of the first of all. Let's think of the two dependent binary outcomes at those level x. Okay. So this idea is motivated from Gregory and Fedorov. He's in here. Then and Wu. Okay, so this is given. This is motivated by them. Okay, so first of all, let's consider that two dependent binary outcomes. Okay, so U for efficacy and then B for toxicity. So we have four possible outcome probabilities in here. So P11, so yes, there is the efficacy. Okay, and there is a toxicity. P10, there is efficacy, no toxicity. P01, no, there is no toxicity, no efficacy. Yes, we have a toxicity. And the P00 is there is no efficacy, no toxicity, right? So we have four possible outcomes, and we can have the marginal probability distribution in here. Okay. Then we can define the outcome probability like a function of those level x. Okay. So y star and z star is the cutoff value. So especially y star is the cutoff value of the efficacy, and then z star is the cutoff value of toxicity. Okay. Then in here, the function of f, y, and z, I will explain about that. The function is the bivariate Weibull distribution. Okay, is it clear? I think it's clear. Then let's think of the next question is why is the bivariate Weibull distribution is useful or important? Okay, so let me explain that. Why should we use the bivariate Weibull distribution? Okay, first of all, this is very natural. Okay, why? Because the dose level is always greater than 0 and less than infinity. So this is a pretty much natural idea. Then second is the flexibility. I will show the model later. Then in my model, the bivariate Weibull distribution contains 6 parameters. Okay, then we can add more covariates depending on adding some regression terms. So at least we have 6 parameters. Okay, so I will show that some plots. Okay, let's see this. Let's take a look at this plot. So first of all, bivariate exponential distribution. Okay, when sigma equals 1, then we can see that the red line is a probability of efficacy. Yes, we have efficacy, given those level x. And then P10, yes, we have efficacy but not toxicity, given those level. And then blue line is the probability of toxicity. Okay. So based on the range, those range from 0 to 100, I think this is natural. Then this case, the green line, let's focus on the green line. This is the increasing function. Then I just change the sigma, just one parameter. All the other parameters, they are same. The sigma is 1 and sigma is 1.2. Then now we have a bivariate Weibull distribution. Okay. 1.4, 1.6, we have up and down in here. And 1.5, 1.8, sigma equal 2, especially sigma equal 3. The green line is the decreasing function, right? So this is a very rich. So what is the important thing is the bivariate Weibull distribution has the various shape of the distributions. Okay, so this is one of the points. So flexibility. Okay, then how can you construct the bivariate Weibull distribution? So before I explain that one, let me just explain the general method. Generally, how can you just construct the bivariate distribution? Okay, usually people use the two methods. First one is the conditional probability. Okay, so what if we have a conditional probability with marginal function? We can just combine them. So function of the joint distribution is marginal distribution times conditional probability, right? Okay. Then second case is the Kapila method. So using Kapila, we can consider dependency. Okay, so this is one of the methods. So I will use the two of them, both of them later. So start with the independent case. Let's think of the independent exponential distribution. What if T1, T2, they follow the exponential distribution, then let's just consider that. What if T1 failed first at time small t1, and the T2 has not failed yet? Then probability gonna be, we can see like this one, beta 1 times e to the power negative b1, beta 1 plus beta 2, and small time t1. Okay, let's consider this one. Let me just rephrase this one. Then probably that t1 fails first at time t1, then t2 has not failed yet. Okay, this is given like this one. Then let's specify the one more of the distribution. Then probability density of t2. Okay, let's think of t2. The given that t1 fails first at t1 is, okay, then the beta 2 prime, let's consider the new parameter beta 2 prime times e to the power negative b2 prime and the t2 minus t1. But we have the condition in here, so t1 is smaller than t2. Okay, so mathematically you can easily prove this one. Okay, just a simple algebra. Then a joint distribution function, t1 is small t1 and the t2 is a small t2. So we can just combine them. Part 1 times part 2, we can have that, but we have the one condition in here. So t1 is smaller than t2. Okay, that's just simple algebra. Then in the same way, we can also consider in this case t2 is smaller than t1. Okay, so just simple algebra, we can just compute it like this one. So that is, so let me just give you a summary of them. So bivariate exponential distribution depend on t1 and t2. So we have two types of the bivariate exponential distribution in here. Okay. Then actually Marshall and Olkin, they consider new bivariate Weibull distribution using Kapilas. Okay, using the Kapila function, they consider dependency in here. Using the beta 3, the maximum, the t1 and t2, using the dependency, they just construct a new bivariate exponential distribution. Okay, using this one, Prof and Stuller, they combine two ideas. Okay, the first idea and then the conditional probability idea and the Kapila's method combined together. They just consider new bivariate exponential distribution. Okay, so one thing difference between this model and the first model is, in this case we consider the third case. What if t1 equal to t2? Okay, then they just construct a new part of them, the part of the distribution in here. Then simple algebra, let's just recall that transformation. Using power transformation, what if t1 follows the exponential distribution and t2 also follows the exponential distribution? Then using the power transformation, y and z will follow the Weibull distribution. Okay, in the same way, we can just make the bivariate Weibull distribution, right? Using the power transformation. So this is my model. Okay, using this distribution, I add the bivariate regression terms. Here we have the 4 covariates. Okay, looks like this. They will follow the bivariate Weibull distribution. Right? Okay, let me show that this once again. Then outcome probabilities P11 is given like this. So once again, Y star is the cutoff value of efficacy, and the Z star is the cutoff value of toxicity. Then we have 4 possible outcome probabilities in here. Then when you just compute the marginal distribution, marginal outcome probability, we should be careful about that. Because using a double integral, since we have the 3 different cases of the functions, okay, in the Bivariate Weibull distribution. So what if cutoff value of efficacy y star is greater than cutoff value of toxicity g star? Then we should use the 3 different types of functions in here. So first of all, y is greater than less than z, y is the same as z, the y is greater than z. We should use the 3 different functions in here. But however, in this case, y star is smaller than z star, we can use just 1 function, right? That means we have 2 possible information matrix later. Okay, why? Because of the integration is different. So in this case, you can see this one. So for example, probability of 1 and 0. So there's a probability of efficacy, but there's no toxicity, the given dose level. Then you can see that we have 2 indicator function in here. Okay, depend on the cutoff value, which one is bigger, which one is smaller. Then we have 2 possible probabilities. In the same way, the marginal probability also we have like this. Okay, the probability of, yes, we have efficacy given dose level. Okay, P dot 1, we have the probability of toxicity, the given dose level x. Then now let's think of the information matrix. So first of all, before we started off the information matrix, let's think of the likelihood function. Then, as you know, the likelihood function is defined like this. Then take a look. Okay. Then since P11, we have some very good relationship. P11 is 1 minus P10 minus P01 minus P00. Okay, using this one, let's make the first derivative, the matrix of first derivative. So in this case, in my model, I have 10 parameters. Okay, so this is kind of one of my problems, but I will ask you later. So I have 10 parameters. Using this, I can just simplify that. We can just simplify it. We can just find the matrix forms. So what if A is like this, and then B and C, we can do that. We can just make the matrix forms of the partial derivative. So once again, the A times matrix A times matrix B times matrix C. This is the first matrix form of first derivative, first partial derivative by 10 parameters. So this is 10 by 10 matrix. Okay. Then, by the definition of the information matrix, so that is expected value of A times B times C, and times transpose of the matrix A times B times C. Okay. Then in here, just C, A and B. Let me show that once again. A and B, they don't contain the random variable, but just C contains a random variable. So take an expected value of C times C transpose. Then, as you can see, I just defined this as D. You can see we can really have a very simple the form of the D. Is the expected value of matrix C times C transpose. Okay, so we can define the information matrix. Okay. Since you, as you know, the binary outcomes, so you follow the Bernoulli distribution, and B also follows the Bernoulli distribution, so we can easily compute this one. So rest of this project, first of all, this is my kind of problem. So I need to find some canonical forms, so find a simpler form. Since I have 10 parameters, so that is a big problem. So I need to find I need to reduce the parameters. So that is one of my problems. So I hope to get some answer before I leave in here. Then second part is I will just come to the design point, the optimal design point. I'll find that. Okay. The third case I will consider about the penalty function. Okay. So this is the plan of rest of this project. Okay. Any question? Thank you.
Are there any questions? Larry.
That's minor comment. So you introduce Weibull distribution to
Yes.
bring some flexibility.
Right.
And of course, it's a relatively complicated distribution because you have a lot of non-linear parameters. Why not instead of but you use predictive function, it's very simple. You use θ1 plus θ2x, something like that. It's linear.
That's right,
Yeah. So why not, did you try to compare that and you brag a little bit that Weibull distribution is very flexible. But what if I introduce instead of θ1 plus θ2x, I will consider θ1 plus θ2x plus θ3x squared.
So more,
And then I will have less, and I will use exponential distribution, very parsimonious. And so I will have less parameters, but I'm not sure that I will have less flexibility. Because with this θ2, θ3 times x squared, I can do quite a bit of things. It's first comment.
I didn't quite understand it. How did you get less parameters by adding more covariance?
Because maybe it's smarter model. But it should be checked. I cannot say it for sure. I say maybe. So I'm not sure. But it's obviously I can get all these types of, you see, curve playing with second order predictive function.
Okay.
Now. And this, by the way, and then I can make the next step. When I have, say, instead of x1, one drug, I have x1 and x2. And then introducing a little bit more sophisticated predictive function. Now I can introduce interaction and quadratic term. I can get the same flexibility, say, with Weibull, with exponential. And I can take all integrals analytically. I think in Weibull maybe you can do it as well, but I just don't remember. Did you think about
You talked about the bivariate exponential?
Bivariate exponential.
No, the bivariate in space of doses.
Right.
There is bivariate in the space of responses.
In space of responses, yes.
Well, actually, I didn't consider about that part, but yeah, that's a good idea. I should
But
think about that.
No, but there is just like in your probit model, you transform from, you start out with a multivariate normal distribution and you transform to the normal, the standard normal, with the exception of the fact that you still have your correlation term in there. I think he can do the same thing with the Weibull model and transform to the bivariate exponential, which.
I don't know. In normal case, everything is clear. That correlation or dependence is easy to in probit case.
That's right.
It's easy to describe. So, and of course, I like your approach to this conditional. It was used. You made references yourself to introduce dependence through conditioning. It's a good idea. Because obviously efficacy can depend upon toxicity. If you have bad liver, you have less chances to survive. Obviously dependent. So otherwise it's interesting, but consider what I said.
Yeah, thank you.
I should say that part of the motivation goes to Ingram Olkin, who, of course, has done a lot of work with these kinds of models, but in particular, whenever I mention to him that we're modeling, we're using a logistic or a probit model, and the variable is dose, and I say, well, we just take the log dose. He has a fit. It's one of his buttons, is that that it would make sense to use a model for which the range of the dose is natural. And so it was part of that got us to think about this. And my first thought is it's going to be a whole lot more complex than the probit, but it still might be interesting to do. My second comment was that for physicians and toxicologists, people that are used to using the logit and the probit, I can't really imagine changing them societally in terms of what they're going to prefer to use. But it may actually appeal in the engineering community, where instead of talking about toxicity and efficacy, we talk about failures from, one system and another system. And since they're used to using the Weibulls all the time, this actually could be more attractive to them as a community.
I think clinicians use, of course, simplest case. When it's exponential, it's time to event. It's everyone, a lot of people use. Only there is an additional problem that you have censored observations. And then it's not that easy to write down information metrics. Of course, after you dichotomize, everything getting easier, but I do not understand, first of all, why I didn't consider continuous case, and then moving to dichotomized case. If you introduce Weibull, so it's time to survival.
Yeah.
And that's all,
Yeah,
or time
that's
to
right.
event.
Yeah, that's right.
And not time to survival time. So,
So we'd like to do that too.
but in this case, it's important that observations are censored, and unfortunately, you do not know how many people will be censored. That is a problem which people face over there when they try to do experimental design. Otherwise, interesting presentation. Thank you.
Thank you.